Okay, let's start. I know that we are starting 6 minutes late, so I can finish at 12:51. Then, okay, so I see a couple of people got scared maybe of yesterday's lecture. So today we will have the first half will be will be also be a little bit of concentration of things, though it's, the end of what we said yesterday. And then we start with the superstring, and we start back again with nice and simple things that you can follow completely. And I don't have to say you have to trust me here or there. So yesterday we finished writing the Polyakov action. So for strings in a background metric, B field dilaton. And I said for the gauge field, but we didn't write it yet. And there were many questions. So many questions about the string being the source of the metric. But that's, and so how do you see strings in a background metric? But that's exactly how you see a point charge in an electric field. The point charge is a source of an electric field, but the way you see it is a probe point charge, electric charge in a background electric field created by other charges. So that's the same. You can see so when we write this Polyakov action in a background metric, so you have to think of this background metric as created by other strings, and this is a probe string in that background. So that's exactly the same. It's just that, we're used to electromagnetism. We're not used to, we're used to the electrons and the photons. We're not used to the gravitons and gravity in that way. So the action, well, I wrote it in Minkowski signature. So the part square root of minus h alpha beta, plus epsilon alpha beta, G mu nu, plus epsilon alpha beta, B mu nu, d alpha x mu, d beta x nu, and then the dilaton had this weird coupling, so alpha prime, square root of minus h, are so the Ricci tensor of this metric H and the dilaton. So people asked, okay, this Polyakov action I understand because I start from the Nambu-Goto action, which is the area of the worksheet, and then I introduce this H, and then I get this Polyakov action, so I can make sense of it. But what about this action here? And the way you can, I already mentioned it yesterday, but now I'll do it more properly. The way you can understand this action is exactly, so the B mu nu part of the action is like the one-dimensional version, or is the, or let's say, two-dimensional version of the coupling of a point particle to a gauge field that is a one form. So it's a two-dimensional version of the electric coupling. So if you have a charged particle that is a source or that couples to some gauge field mu, then the way you write that coupling is by a charged particle of charge q, and then you integrate over the whirl line. So it's a particle moving. So the whirl line that we talked about, and then this is a mu dx mu d tau d tau. So you integrate over the parameter along this wear line. And this is the way you write the coupling of a charged particle or a charged particle in a background field where this charged particle couples to the background field. And again, this background field, I can think of it, this is a probe particle having an electric charge under this field, which is created by other charged particles. If you write it in forms, I don't know if you're used to a form language, more or less. Okay, I'll say a couple of words about the forms when we get to Ramon. But so you can write this as a, or maybe I can say it now. Well, no, let me say it later. So you can write this in form language as Q integral of the one form A along, or I mean, well, let me leave it like this. I don't even need to say this at this point. But if you look at this term is exactly, so here we have dx mu d tau, and here we have dx mu d sigma, dx mu d tau. So it's the derivative of this with respect to the parameters of the work volume. So this is, so the analog, so the 1D or 2D analog, so 1D in terms of the charge, or 2D in terms of, yeah, so well, 2D analog. It's precisely that. It's the integral of, so B mu nu, well, epsilon alpha beta, B mu nu, dx mu, d sigma alpha, dx nu, d sigma beta, and, well, sorry, and that's it, d sigma alpha, d sigma beta, d sigma, d2 sigma, or yeah, the integral d2 sigma. And that's precisely what we have. So it's exactly the analog of this. So this means that the strings, which are one-dimensional objects, they couple to this gauge field, which is a two-form. So a point particle, zero-dimensional, couples to a one-form. A two-dimensional object, a one-dimensional object couples to this form, so B mu nu. And the coupling is, so somebody asked why not a two? And it's very important that the coupling is the same as the coupling here. So, so the 2D analog, it's is this, where here you will have the charge, and the charge is, the charge, well, in this Minkowski signature, you have a minus sign. So the charge per unit length is the same as the mass per unit length. So charge per length is equal to the mass per length, and this is the tension of the string, and this is a property of BPS, what's called BPS objects that I don't know if Dan Waldron talk about that, or he will, but just as I said yesterday, this means that the strings, they attract gravitationally, and they repel electromagnetically, but those two forces are the same. So I mean in magnitude, so they live happily one with the other. So I could have motivated, I mean, I could have said that, and then this coupling would have come naturally. Yes. Yeah, exactly. So, and this B, yeah, as I said, so this B, yeah, the gauge transformation is B plus D lambda, which is a one form, yeah. And,
so it's like a gauge current coupling. So like the alpha X mu, the beta X mu is like current.
Yeah. Mm-hmm. Yeah. Yeah, but this is, so these are external fields that can be, I mean, can be different if they are sourced by, I mean, you can have things, so we'll see the brains. I mean, you have more things that couple, so the strings couple to both, but they are the brains that couple to this, but not to B or B in a different way. But what I'm saying there is that I mean, she is not necessarily equal to B in some sense. So she and B might be generated by sources which are not of that BPS property, but it's the string itself that has that BPS property.
Strings are sources of both, and this is applied. Otherwise,
Yeah, yeah.
turn on.
If I turn on something else that couples, I mean, if this is created by black holes or something which are neutral, then this, yeah. Yes. Mm-hmm. Very good question. So, yes. So, yeah, I wasn't sure whether, so that comes with the coupling with A mu. So I wasn't sure whether I was going to say this, but since you asked, very good. So is this case invariant? It doesn't look like, right? We have a B and we don't have the field strength. I mean, usually in the action we have field strengths, and here we have a B. So what happens if we do, so, I mean, maybe, so everything is nicer in the of forms. So, yeah, I was planning to explain forms later when we get to Ramon, but let me do a parenthesis now. And since I don't want to miss the factorials, let me get the corresponding. No, so I think I know the factorial factors, but just in case. Okay, yeah. So this is a parenthesis. For those of you who don't know, so Antgeludo, I don't know, on P-forms. So a P-form is a tensor, I call it C, that is totally antisymmetric. So this is equal to C, the notation is this. And this bracket means just doing all the antisymmetrizations, and you have to put a 1 over P factorial. So this is C mu1, mu2, mu P minus C mu2, mu1, mu P plus minus. So you put all the, I mean, all the exchanges of indices out such that this is totally antisymmetric. So that's what a P form is. So for example, for a 2 form, C, and the notation is CP. So this is a P form, tensor with P indices. And for example, C2, it's a, so C mu nu is 1/2. So C mu nu is 1/2 of C mu nu minus C mu, right? So there are a few things that will be important for us. So one is a wedge product. So if I do a BQ or CP, I do the wedge product of a P form and a Q form, I get a P plus Q form. So I just have to antisymmetrize everything, but then I have to put these combinatorial factors so that, I mean, this combinatorial factor is there because if the thing is, if C mu nu is antisymmetric already, then this should be equal to C mu nu. So then I have to put the 1/2. So that's why the 1 over P factorial factor. And so the component mu1, mu P plus Q of this is 1 over, so P plus Q factorial over P factorial, Q factorial, and then the totally antisymmetric mu p, and then b mu p plus 1, mu p plus q, totally antisymmetric. I can erase that. Another thing that we'll need later, it's the Hodge star, that from a p form, it gives us a d minus p form if you are in a space of d dimensions. So, and it's defined the Hodge star of Cp is a form that has mu1 to mu d minus p indices. So it's a d minus p form. And this is equal, and again, 1 over p factorial epsilon mu1 mu d minus p mu d minus p plus 1 up to mu d of c mu d minus p plus 1 mu d. So basically, if I'm in 4 dimensions, the Hodge star, and I have a 2 form, the element 1, 2 of the Hodge star of C will be equal to C3, 4. That's, I mean. So it gives the components, the missing components, what I said. That's, another thing we'll need is the exterior derivative. Which for a p form, it gives a p plus 1 form. So, and the components mu1, mu p plus 1 is the p plus 1, not factorial, but just p plus 1. And I have to do is a totally antisymmetric derivative of c mu2 mu p plus 1. So I take the derivative and I antisymmetrize the index of the derivative with the index of c. I think so. This normalization is, yeah, if you wish, it's a convention, but it's the nice convention that, I mean, if you take the Hodge star of this, because this has its own normalization, which is 1 over p factorial. Yeah, I don't see a simple way to, I mean, it's a convention, but it's a good convention for. Yeah, for example, it's a good convention for, yeah, what I'm going to say, for Stokes' theorem. And the nice thing about this is that if I replace this partial derivative, then the Christoffel symbols in this antisymmetrization go away. So this is really a p plus 1 form. So this is really a covariant object. So this is equal to p plus 1 covariant derivative. So usually if you do the partial derivative of a tensor, it doesn't transform as a tensor. You need to add these Christoffel symbols, but if you are antisymmetrizing the partial derivative, then it does transform as a tensor. So this is a p plus 1 tensor that transforms as it should. I mean, this is equal, I think. So. Yes, sorry. Yeah, the Christoffel connection. Yeah, if you take a connection with torsion or something like that, yeah, that's not true. Yeah. And know that d squared is equal to 0, because if I put a second derivative, then it's symmetric in the two indices of the derivative, but here I want to make it antisymmetric. So it's a nilpotent, let's say, nilpotent operator. And then I need two more things. That the integral of a d-form, so in d dimensions, is coordinate invariant. So just doing the x of a, some form. Yeah, I change between a, c, you understand. 0 up to d minus 1. This is, I don't need to put any square root of minus g. You just do this, and this is coordinate invariant, and this we just write as integral over c. Integral of c d over some d-dimensional surface. And one can also do a d-form or a p-form, also for a p-form. The integral on a p-dimensional submanifold is also coordinate invariant. Invariant under diffeomorphisms. That's it. And that we write as the integral of Cp over some p-dimensional manifold. And that's coordinate invariant. And the last thing I need about forms is Stokes' theorem. Stokes' theorem that the integral of d, so the integral over a p-dimensional manifold of the c p minus 1, so the exterior derivative of a p minus 1 form, this is a p form, so this is fine, this is coordinate invariant. And this is the same as the integral of c p minus 1 over the boundary of this manifold. So that's Stokes' theorem, but in p dimensions. Okay. Okay, good. So now back to our known and loved Polyakov action, and the question whether this is gauge invariant. And now I can answer this question in terms of forms, so it's much nicer. you don't get all these dx, d alpha things. So is the Polyakov action invariant under gauge transformations of the B field? So under B going to B plus D lambda. So now I can write this. So B, you can call this B2 and D lambda 1. So the gauge parameter is a 1 form, B is a 2 form. And we say it's a gauge field, so it has these gauge transformations that came from the null states in terms of the quanta of this B field. And it doesn't look like, so let me write so the part of the Polyakov action corresponding to the B field. So it's minus T over 2 integral over the worksheet of B, right? That's what it is, this whole thing. So under this gauge transformation, this goes to B2 minus T over 2 integral of the lambda 1. So integral over the worksheet. Now you can tell me if this is invariant or not. We can use the Stokes theorem. So this is minus T over 2 integral of the boundary of the worksheet of lambda 1. Very good. And now yeah, I see people doing this and that. Does the worksheet have a boundary? Yes, no, you're both right. So it depends if it's an open string or a closed string. A closed string doesn't have a boundary, so this is equal to 0 for a closed string. But for an open string, it has a boundary. So I mean, it has two boundaries, right? One at, so now let's forget about conformal transformations and disk and loops. Let's just do simple worksheet of an open string. So it has two boundaries, one at sigma equals 0. But I mean, yeah, I shouldn't put this. So this keeps going, right? Sigma equals 0, so one boundary is sigma equals 0 and sigma equals pi. So then the part of the B field of the Polyakov action goes to itself minus T over 2, the integral. Now let's write that explicitly. So that means that means a derivative. So that means lambda mu d. So it's like here, lambda mu dx mu d tau d tau. So the integral over d tau, and this at sigma equals pi minus at sigma equals 0. And now is this 0? Yeah, exactly. Depends on the boundary condition, right? If the boundary conditions are Dirichlet, then this doesn't depend on tau. So this is okay. For Dirichlet boundary conditions, but not for Newman boundary conditions. Because Newman boundary condition was that the derivative with respect to sigma is equal to 0. And here we have the derivative with respect to tau. So what you get is for an open string, with Newman boundary conditions, I mean, for close, so close, and Dirichlet boundary conditions, the action is invariant. For the open string with Newman boundary conditions, I get that SB goes to SB minus T over 2 integral of lambda mu, lambda, how should I call it? Let me call it M dxm d tau, where M are the directions that have Newman boundary conditions. Right, those are the only ones that have this derivative non-zero. So this sigma equals pi minus or plus T over 2 integral of lambda m dxm d tau. Okay, and now I'm done. I cannot ask you. This is not zero. So how do I make this 0? And so I'm motivating the next thing, which I could have said, this is how it goes. But the way you make this 0 is to couple these endpoints of the string to the gauge field, and then have a mixed gauge transformation. When B goes to B plus D lambda, this A goes to A plus lambda, or minus lambda. So let's see the signs. So this is this is gauge invariant if there is a coupling to some AM along the directions where we have Newman boundary conditions. So remember, we can think of these branes, and it's not that we can think, there's really a brane along the directions where we have Newman boundary conditions, and here we have Dirichlet boundary conditions. And the coupling to AM, so is A is minus T over 2 integral of A. I can write it just integral of A now, because, so this is at sigma equals pi. So at one endpoint of the string, so by this A, I mean AM, dxm, d tau, right? So I write it as the integral of a one form. And then plus T over 2, the integral of A at sigma equal 0. And then I say that whenever B goes to B plus D lambda 1, B2 goes to B2, A should go to A. So I want to cancel that term, so minus A should go to A. So A1 should go to A1 minus lambda 1. So it's a gauge transformation on B that induces this transformation, which is not a typical. So the gauge transformation of A is by a zero form. A going to A plus d mu lambda. That's a usual gauge transformation. So this is a shift of this field. And it's such that it absorbs this gauge transformation here. But what is this saying? Okay, I add that by hand, and if you compare to this is saying that the endpoints of the strings are charged under this field. So somebody had asked, maybe it was, I don't see, and I don't know your names. Maybe it was you who also, what's the source for this? And I said the endpoints of the strings. So here you see it. So this is, this here is the coupling, or let's say so, well, coupling of the endpoint of the open string to this gauge field A mu, or AM, the one along the brain. So the source for this are the endpoints of the string. And again, the charge is also proportional to T. So one can say T times pi or something like that to make it not a charge per unit length, but a real total charge. This is the length. Yes. I mean, it's just that if it's not gauge invariant, then you cannot say that this is a gauge field. You have open strings, and this breaks this gauge invariance, but that's not what happens. So you have the open strings, you have Newman, and actually Newman boundary conditions, you always have, you cannot have a, so not having Newman boundary conditions means in any direction means you have a d minus 1 brane. I mean, also in time. So that's very weird. So that's a d instanton, and we're not going to talk about that. So you always have some Newman directions for Newman boundary conditions. And in the type 1 string that we will talk about, which is open strings, well, I'll talk more about that. But yeah, there's always some Newman directions where there are Newman boundary conditions. Yes.
I guess under gauge transformations, the gauge field A shifts by exactness, right?
Yes.
So that means lambda is d of something, but here we have b shifts by d of lambda, so you get b squared.
Sorry, you say if A goes to A plus D something. Yeah. So B doesn't transform. So there's, and then on top of it, there's the gauge transformation. So there's another gauge transformation. So this transformation is okay. A1 going to A1 plus the, let's call it lambda tilde, and this is a zero form. This is a scalar. And that transformation is okay. Because now these endpoints don't have a boundary. So now so this is this. I'm integrating over this, and this doesn't have a boundary.
How should one interpret this transformation?
This is this one here. Yeah, so it's saying, yeah, I don't think I will have time to talk about this, but when you write the D-brain action, then whenever you have the field strength, so now, then the field strength, so I guess your question is F2, which is dA. Now it's not gauge invariant under this transformation. It goes to V2 plus D lambda 1. So what happens in the brain action is the combination that you have, the gauge invariant combination is F2 plus V2. That's in the brain action you combine these two. And now this is, so we wrote the P-brain action in a background metric, so that was the generalization to P dimensions of the Nambu-Goto action. But that has to be completed into what's called the Dirac-Born-Infeld action, and it has this combination of F2 plus V2. No, I guess it's not irrelevant, but I don't know the answer to that. Well, another thing in my list to think about, but no, I guess it's not irrelevant. Any other questions to put in my list? Okay, so now, okay, we're happy with this part. Now the last part, well, I wrote it here. So you have to add the coupling to the A field is that. And now I wanted to see the things to say about the coupling to the dilaton. Or let me call it S phi. So the Polyakov action, the part that depends on the dilaton. So now let's take constant dilaton, because our life is complicated if the dilaton is constant. So phi of x equals phi 0, constant. Then I can write, so I can take it out of the integral, and S of phi, or S of phi 0, if you want, is t is 1 over 2 pi alpha prime. So t over 2 alpha prime times minus t over 2, this is and let me put it in, so if you use Euclidean signature, that minus becomes a plus. So this is 1 over 4 pi integral of d to z, and I have the dilaton, so phi 0, integral of d to z of square root of h, r of h. Right, I just passed to Euclidean signature. And R, that Ricci tensor the Ricci scalar is a Ricci scalar of this metric H. Now, you should recognize this without the phi 0. Yeah, I think you're saying that. This is the Euler number, right? So this is phi 0 times chi. Now if I make the worksheet, so far we were looking locally at the worksheet. If I make the worksheet a global thing, so if I take, I compactify it by taking the points, the worksheet from minus infinity to infinity, then the dilaton coupling gives me the Euler characteristic. So it's the dilaton, the vacuum expectation value of the dilaton, times the Euler characteristic of the worksheet. And now we go back to the point that in the closed string, adding a handle, so every time you add let me draw it like this, which is adding a loop. So this adding a handle, which is equal to going from adding a loop. We said that delta chi was equal to -2, while in the open string, you add a boundary, and then delta chi is equal to -1 in going from the thing with p loops to the worksheet with p+1 loop. So now if I have e to the minus in the path integral, if I have e to the minus Polyakov action and the part that corresponds to the dilaton, and the dilaton is constant, or I can split it into a constant piece, a vacuum expectation value, and a fluctuating piece. And the part corresponding to the vacuum expectation value gives me e to the minus phi 0 chi. So this means that when I go to, when I do this path integral for a loop, from p loops, or let's say adding a loop, I get this extra factor of e to the, so for the closed string, let me write it here. So for the closed string, I get an extra factor of e to the 2 phi 0, and for the open string, I get a factor of e to the phi 0. But if we look at diagrams where with this handle is not very nice, but so I mean, what are we doing here? We're adding an extra 3-point function when we add. So if we write it in terms of the Pans diagram, suppose the tree level, and here I have. Yeah, I'm so bad at drawing that I'm not sure this will. Or maybe let's go here. But what do? You also a coupling constant here and a coupling constant here. So this adding a handle also is. So this means also adding a G string square, a coupling constant that we haven't talked about, that I'm going to call it G string square. And if we do, or let me call it G closed, G string close square. And if you do this, it's the same, it's G square, but open. The coupling constant for the open string. And now if we go here, so then this means that this is G close square, and this is G open square. So G close that we call G string is not a free parameter, but is, so this is e to the phi 0. So it's the vacuum expectation value of the dilaton. So that's why it's not a free parameter, it's a vacuum expectation value of a field, which is something you're not used to in quantum field theory. And G open is the square root of G string is e to the phi 0 over 2. Or G close is equal to G open square, which also makes sense because to make a closed string, we do the tensor product of two open strings. So I mean, this makes a lot of sense, yes. It can fluctuate around 0, and then you are in bad shape because it means you're not in perturbation theory. G is equal to 1, and you cannot do perturbation theory. But yeah, you can perfectly do that, and good luck with. That's a worse situation, because if it's very strongly coupled, then one can do a duality and see things in S duality and see things as weakly coupled in another frame. But yeah, when this is one, it's yeah. No. So yeah, you can trust. So everything we've been doing, you can trust if this vacuum expectation value, or e to the phi, so phi 0 is negative, but let's say, so if e to the phi 0 is very small, yes. But I mean, there is this story of moduli stabilization, and oh, I thought I was done, but I'm not done with this. Okay, I will say a couple more words about that. Yeah, maybe I started at 5, so I can take 5 more minutes, so that then we do the break, and then we start with the superstring. Yeah, there was. Mm-hmm. So, I mean, where is the dilaton? Where? So here, so whenever I want to do scattering amplitudes path integral, I have to put e to the minus the Polyakov action, the whole thing. So that thing, yeah. So there you have the coupling to the dilaton, and because because adding a loop, whenever you add a loop, so I mean, this is the same as in. Yeah, because the other, it's so this is. I mean, now this, if this phi is constant, now this is independent of x, and when you do e to the minus s, I mean, the rest will be integral of dx, integral of over dh, and complicated things. But this part is some constant thing, and it gives you some number, which is e to the, I mean, the topology of the. So the Euler number of the worksheet times this phi 0. While the other thing is the whole thing that you have to integrate the x. And if you have a web for phi and a fluctuating part, the fluctuating part will enter in this horrible thing. But so when you do scattering amplitudes, you have these sum over loops. And then each loop will be weighted by this factor. I can take it, I mean, I can say that phi is a phi 0 plus some phi, so wave plus some fluctuating piece around this phi 0. And the fluctuating piece will stay here in this integral horrible, but the wave gives this that. And yeah, and the fluctuating thing is some coupling constant that varies along space. So it's a complicated thing that you know how to treat in some cases, but yeah, in general, it's a difficult thing. And it gives some, so it gives some interaction term to the same as if the metric is non-constant, the B-field is non-constant, it gives some interaction, could be horrible interaction terms that you don't know what to do with. Yes. No, it doesn't transform. So what transforms under the conformal symmetry or the Weyl symmetry. So you can do conformal transformations of the alpha and beta, but there are no alpha and beta indices there up to the integral, and doing conformal transformations. I mean, is a symmetry, but and yeah, and the whole, so this whole action, because of the action of H and R, then so conformal transformations can be absorbed by Weyl transformations, but yeah, this part doesn't transform, and here the transformation of R absorbs the transformation, so it transforms as e to the minus omega, while H transforms as e to the omega. But phi, if it's so, let me say it better. So this is phi is a function. If phi is constant, it doesn't transform. Sorry, I said that wrong. If phi is constant, it doesn't transform. If phi is not constant, so this part depends on x, which is itself a function of tau and sigma. So that's a transformation. I mean, so it transforms as well. A scalar field. Well, actually, yeah, a scalar field doesn't transform. So, but is the x itself that gets reparametrized. I mean, it's a, so it's a, so, no, because you have a transformation, so yeah, no, I think, so this is, yeah, so that's the motivation for putting this factor of R. So if I put square root of H and phi, that doesn't, it's not Weyl invariant. But, yeah. Eh? Yeah, it's a symmetry. It's a symmetry of the action. If it's not constant, sorry. No, if you have this, no, because the Weyl invariance is transforming H, but I don't transform X. That's the Weyl invariance. So there are two things. There's the conformal symmetry and the Weyl invariance. And these two combine such that the action, so the conformal symmetry is a symmetry because you can reabsorb it in a Wald transformation. So the Wald transformation is H going to e to the omega H, while the Wald symmetry is, conformal transformations is sigma plus going to some sigma tilde plus, let's say, which is a function of sigma plus, and sigma minus going to, so under this transformation, now you have to write x in terms of tau, in terms of tau tilde and sigma tilde, but the square root of h and the d2 sigma makes that a symmetry under any reparametrization. So these are particular reparametrizations. And square root of h, d2 sigma, this is invariant. No, you have both. I mean, it's... So for the action to be invariant, you're saying, okay, I have this, and then I have R that transforms. But R is a scalar under reparametrizations. It's a diffeomorphism invariant. So under diffeomorphisms, no. Yeah, no, it doesn't give you a total derivative. So R goes to e to the minus omega R. And so this depends on the dimensions. This is in 2 dimensions. If h goes to e to the omega h. In general, R goes to e to the minus omega d minus 2 over, no, it's not d minus 2, d over 2, I think, or something like that. You mean if you have this interaction between two open forming a closed? Yes, so that would go with I would say, she open square or she closed, yeah. But the action, yeah, the Polyakov action, so that part of the action is the same for closed and open. So the open string couples to the metric, B field and dilaton in that way, and so as a closed string. And then if you have open strings, you have to add that other extra term in the action. But the part of the dilaton is the same, yeah. Okay, let's take a break though. Then the part that I'm going to say will be pulled out of the hat and it will be fast. I don't want to I mean, the lesson is important, but I don't want to spend a lot of time explaining the calculation. And then, so that should take 5 minutes or maybe a little bit more, and then we start with the superstring. Okay, I'll be quick, but with a very important point. But if you want to look at the calculation, it's done, I'm not sure it's done in Becker-Schwarz, but in David Tong's notes on string theory, it's done carefully, so you can read it there. And those, you have the PDF without having to ask me or buy anything. So what do we do? So yesterday I talked about expanding G mu nu around flat space. Now let's suppose you are really in a curved background that has nothing to do with flat space. It's well, very, very curved. We'll see how. So what do we do with the action? So forget about the dilaton, let's just take the metric, so forget about this. For what I'm going to say now, then I will incorporate them. I will tell you the result. So what do we do? So as we said, G mu nu depends on, so if this is a constant, if this is eta mu nu, then these are free fields. If this is in general a G mu nu of X, this brings some horrible interacting thing. So what to do in that case? So there are different ways to go. The usual one, which works in some regime that we'll see, is to expand G mu nu, or so the axis of tau sigma. There is a center of mass term. And then, well, let me forget about the center of mass position. And then the y mu's of tau and sigma, which are the oscillations. Let me do a string that is has 0 center of mass momentum. So then what you do is expand. So G mu nu of X, d alpha mu, d alpha X mu, d beta X nu is equal to G mu nu of X0 plus G mu nu rho, covariant derivative with respect to rho, at X0 times y rho. This is the part that, these are the oscillations, plus 1/2 of G mu nu rho lambda, y rho y lambda, plus expansions, and then this is the alpha y mu, the beta y nu. So when does this expansion, or truncating this expansion, when can I do it? Well, I can do it whenever, so these are the oscillations, so the scale of this is square root of alpha prime, right? And the scale of this is the scale of variation of the metric. So that typical scale is the radius of curvature. So, or the Ricci the Ricci scalar. Sorry, and what I want to do is this. So this is radius of curvature. If you have a sphere, the radius of curvature is the radius of the sphere. So if this is much less than 1, so space-time is varying, but it's varying at scales which are much longer than the string length, then you can do this expansion. So this is good if you have a sphere that is order of the string scale, you cannot do this. You have to attack the problem in some other way. And then you know that one can always choose coordinates such that this is 0. And there are coordinates which are called Riemann normal coordinates. One usually doesn't. In here you don't use them too much, but here are very useful. In which this 1/2 of G mu nu rho lambda is equal to the Riemann tensor minus 1/3 R, and I have to do mu rho nu lambda. So this you can do locally, right? This at a given point is equal to this at that point. It's not that, this is not in general the same as this is. You can do at some point, but you cannot do you cannot do everywhere. So then what I get here is a term like, so I get a term like R mu rho mu lambda y rho y lambda di alpha y mu di beta y nu. So this is some, and this is at x0. So this is some constant tensor. So this is some interacting, two-dimensional interacting field theory that has this 4-point coupling YY dy dy. And you can do, so the calculation I'm not going to do is to do this, sort of try to do dimensional regularization of this, going 2 plus epsilon dimensions. And so if you do this, so I mean, do this in 2 plus, so the action, so the integral of the action d2 sigma square root of minus h, whatever, if you do this in 2 plus epsilon dimensions, and you do a Val transformation, you replace this by the propagator, blah, 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 you can see the calculation. But what you will get is under Val transformations, this is not invariant. This goes like R mu rho lambda, sorry, R mu rho nu lambda eta of x0 eta rho lambda the alpha y or dy dy minus one term that is divergent sorry, this is the original term y rho y lambda, and then minus one term that is divergent. So if you put the propagator here, what you have is eta rho lambda. So you contract this index with this index, and you get the Ricci tensor dy dy. Okay, so look, calculation in chapter something of Tom. Chapter, I don't remember, of Tong's lecture. And then we will have to one will have to add a counter term to reabsorb this infinity, but we don't like counter terms. So this infinity doesn't appear if R mu nu is equal to 0. So if we want this Weyl transformation, so Weyl transformations are a symmetry of the action at the classical level, but if we want the Weyl transformations to be a symmetry at the quantum level, our symmetry at the quantum level, if, R mu nu is equal to 0. And this is at order alpha prime. If you go in higher orders, you get extra, you will get some alpha prime square. It's not zero, but you will get some alpha prime square correction with derivatives. But, so, and this is an equation for the space-time metric. And actually, this is Einstein's equation if you don't have energy momentum tensor. So we are recovering Einstein's equations. For T mu nu equals 0. So we recover a space-time equation from requiring Wild transformations to be a quantum symmetry. So that's great. And the lesson is you cannot really put any metric that you want. I mean, first, you don't know what to do, but more importantly than that, if you are in this regime, if you are in another regime, then you have to treat this differently from the conformal field theory point of view. So I will say a couple of words about that. But if you are in this regime, you can work with this. This will be fine, and this will be while invariant. A loops is if you have this equation. So the metric has to be Ricci flat. This is called Ricci flat. And Ricci flat doesn't mean flat. There are many spaces that have Riemann tensor different from 0, but are Ricci flat. Compact spaces. Compact spaces. So that's a very nice thing about compactifications is that there are compact spaces which are Ricci flat, but not flat. So you have to require that beta function is equal to 0. So very good. So I'm going to write. So that's a beta function for the metric. And now let's introduce back the B field and the dilaton, and one could in principle do that same calculation. And you get a beta function for all those couplings. So the beta function for the metric is at order alpha prime. So then it gets corrections. Is the Einstein equation. But now the derivatives of the dilaton and the H field, which I haven't said, but this is the field strength of the B field. Order of alpha prime square, I mean, it's order of, I mean, this is the parameter. So this acts as an energy momentum tensor if you have the dilaton varying. So the space-time doesn't have to be necessarily Ricci flat. If you also have a dilaton that is varying and you have a gauge. So H3 is dB2. It's a field strength for the B field. Then the B field gets its own, also its beta function, which is, well, the precise form is not important, but okay. Let me write it since I'm taking more than 5 minutes. So, mu nu plus order of alpha prime square. So this is Einstein's equation. Well, let me write the three of them. Yeah, you're right. Lambda, thank you. Yeah, thank you. And the beta function for the dilaton is alpha prime minus 1/2 Laplacian of the dilaton plus d rho phi minus 1 over 24 h mu nu lambda h mu nu lambda plus d minus 26 over, well, 6 alpha prime or whatever. The two terms are the same. You're right. The derivative goes on. Thank you. Very good. You're paying attention. Very good, very good. Yes. Yeah. Because this is, I mean, I'm making everything, so everything is dimensionless with that alpha prime. So this alpha prime with that alpha prime, you get a d minus 26. And yeah, 0, a constant term. Yeah. I wrote it like that. And no, sorry, and I'm, no, yeah. Yeah, I wrote it like that. Yeah, I should write d minus, actually I have it first here, and which makes more sense. Yeah, so this appears here, and then you have a, without alpha primes, and then you have the rest, which is order alpha prime, indeed. Yeah, so this, you should write it as I had it in my notes. So this is an order 0 term. So this is Einstein's equation. This is the equation of motion for H. So it looks if in electromagnetism you get the derivative rho of F rho mu equals 0. And here you have, so if the dilaton is not constant, it acts as a source. But so this is the equation of motion for B. And this is an equation of motion for the dilaton. So you get equations of motion for all the fields from requiring Weyl invariance of the Polyakov action. And then note this term, which indeed should be a 0th order term. If this is not 26, then I have to balance this term with some derivative of the dilaton or some H field. But this means that the dilaton should vary in scales which are 1 over square root of alpha prime. So I'm not really in this regime where the variation, so this is radius of curvature variation of the metric, but this variation of everything. So this expansion makes sense where the variation of everything is, so everything varies in a scale that is much larger than the string scale. So if this is not equal to 26, which is called the critical dimension, so there are solutions which are fine. So d equals 26 is called the critical dimension. And then this term is not there. If you're not in the non-critical strings, which are not in d equals 26, have, for example, there's a solution, but it's a conformal field theory because now you cannot really see it as a solution of this, but it's called linear dilaton, CFT, in which the dilaton is linear with the coordinates. So the dilaton, so phi like x over square, I don't know, some contraction, I don't know, x mu. I mean, this is very, very roughly, but the important thing is that it varies. No, linear dilaton, it should be. So how does it work? Oh, I have it here. Well, in any case, so yeah, let me write it like this. But in this linear dilaton CFT, so this CFT, you have to analyze it with CFT techniques and not this. So not these equations don't make any sense because this order are, the next orders are the same order as the one I wrote. But just to tell you that equals 26, and this has its own central charge, so the non-critical strings that will have non-critical strings with the ghosts plus this thing, the total thing will have central charge 0, so you can do that. But we'll stay in the critical dimension 26 for the bosonic string, or 10 for the superstring. Yes. That interaction. So we are expanding, so we are saying now the metric, I'm not in flat space, I'm in curved space, and we are expanding the metric around the center of mass position, and then this is what you get in that expansion. And then you get terms with y to the 4, or I mean y cube, dy, dy, you get all sorts of interaction terms. Yeah. So it's coming from here. So that term there is this term here, the second order. So this zeroth order is, so this is a constant. So having this is the same as having eta mu nu. It's just that I mean, it's rescale the thing, but this is a constant. So this is free fields. This, I mean, just this part is free fields, and then you are adding these interaction terms, which are y. So this is del y del y, and then this is more an interaction term that is y del y del y. Yes. So no, when we can, you're saying, okay. Yeah, I don't know much about this linear dilaton story. I mean, when we quantize the theory, you get that A is C minus 2 over 24. This is what you get. So the A is not equal to 1 if you're not in the critical dimension. But how does it work with the rest? Don't ask me, because I don't know. But yeah, this is the result of the calculation. And then we said A equals 1 is nice because we have massless states, and then D is equal to 26. But actually, this is the derivation of D equals 26 being the critical dimension, the dimension where you have wild invariance if at the quantum level, if you satisfy these equations. Okay, so 51. Okay, let me say 5 minutes. Let me start motivating the superstring. I don't know, I could stop here, but no, this way. Well, no, it doesn't make too much sense. You're motivated for the superstring, right? Yeah, the thing is, I have to see, since we will have 2 classes, I thought we will have a lot more, so I have to see what, because I also want to talk about duality. Maybe, yeah, this is something I can do, okay, in 5 minutes, which can be done in the bosonic string. Okay, you are ready to go. I'm going to talk about T-duality. So let me see if I have my notes. This way I don't, I'm more careful with them. With things. So suppose you have, suppose you have a closed string. And I tell you, take this boundary condition for one of the coordinates, let's say x25 of tau sigma plus pi, and again this, let me take 2 pi. So sigma goes from 0 to 2 pi. It's a better convention. So I say this is x25 of tau sigma plus 2 pi Rm. So I have for x, for all the other x's, I have the normal boundary condition that tau sigma plus 2 pi is the same as x in tau sigma. But for this, I have this weird boundary condition. So when can we have this weird boundary condition? Right. If I have a circle, so let's say the other coordinates are this boundary condition is saying that the string winds around the circle m times. So this m is a winding number. And it's a topological number. It should be conserved if you do interactions. And what you get is, so the expansion in most that you get, so there's also